Hey, good morning everyone. So now we are going to discuss about ring counters of digital electronics. Okay, from our fifth unit. So already in our last class we have discussed about what counters and types of counter is also over. How many types of counters are there? Two types of counters are there: synchronous as well as asynchronous counters. And while coming to the next one, modulus of the counter and mod 3 counter, mod 10 counter, decade counter, the synchronous counters over, and also synchronous up down counter is over, synchronous down counter is also over. So while coming to the counters, what is the use of counter? Once I would like to revise few points from the last class. A counter is a device which is used to count the number of clock pulses appeared at input. And while coming to the type of counters, counters are basically of two types: synchronous counter as well as asynchronous counter. So what is the main difference between synchronous and asynchronous? In synchronous counter, all the flip-flops are triggered with the same clock pulse simultaneously, and in asynchronous counter, the clock pulse must be applied to the first flip-flop, and all other flip-flops are triggered with the output from the first previous one. And while coming to the next one, okay, means synchronous counter, all the flip-flops are triggered at the same time. So cause of next stage out flip-flops triggered with the output of previous stage. In asynchronous counters, it will provide more propagation delay and the asynchronous counters become slow. Okay, and while coming to the synchronous counters, they triggered at the same time with same clock pulse, so the propagation delay must be reduced, the system becomes speed. And while coming to the modulus counter, the modulus means what? Means the ability of the counter to count how many number of states. Okay, the ability of the counter to count the number of states is called what? Modulus. And while coming to the modulus, what is meant by mathematical expressions of modulus? Means 2 to the power of n is greater than that of modulus. Here modulus is indicated with n. So simply modulus means number of states, number of output states. So here 2 to the power of n is equal to, so in modulus counters they follow the formula 2 to the power of n is greater than or is equal to n. So here this capital N indicates number of output state and the small n indicates number of flip-flops. So based on this formula, the modulus counters are designed. For example, if 2 to the power of n is equal to 2 means capital N is equal to, we are getting how much? If small n is equal to 2 means capital N we are getting 4. That means what? Here number of flip-flops we are using in the counter is 2 and it able to produce 4 states. If n is equal to 3, we are getting 8 output states. If n is equal to 4, we are getting 16 states. So in this way mod counters are designed. So while coming to the 10 is not possible with 2 to the power of 3 and 2 to the power of 4, but here we are considering 2 to the power of 4 because it only will provide greater than n. Okay, we want a 10 but 2 to the power of 4 gives 16, so that 4 flip-flops are used in the mod 10 counter. Okay, and while coming to the mod 3, mod 10 counter, after, for example, if it is a mod 3 counter, after counting of 3 clock pulses from 0 to 2, a third clock pulse, means after counting 3 clock pulses, at fourth clock pulse, the output should be returned to 0 by the application of clear signal. Okay, and while coming to the mod 10 counter, the output should be returned to 0 after counting from 0 to 9. At 10th clock pulse, it provides some output. Okay, that means that it is equal to 0. From 0 to 9, it will count. At 10th clock pulse, the output of all the flip-flops should return to 0 by the application of external input, that is clear. Okay, so this is about asynchronous and synchronous mod counters. And the next one is up-down counter. Okay, in synchronous also up-down counter is there and asynchronous up-down counter is there. So both synchronous and asynchronous up-down counters, okay, asynchronous up-down counter and synchronous up-down counter is there. So both are used to provide the bidirectional counting at the same time. So synchronous both provide up direction counting and downward direction counting, but asynchronous is somewhat slower compared to the synchronous. But asynchronous is simple in construction, synchronous is somewhat difficult in construction, but both are able to provide the counting in positive to negative, means 0 to 9 and 9 to 0, 0 to 15 and 15 to 0. Upward direction is there as well as downward direction is also there. And while coming to the applications, the counters especially used in digital clocks. Okay, the counters are especially used in digital clocks and also used in frequency divider circuits. And also the counters are used in digital computers, and the counters are also used in industrial applications. Okay, also used in industrial application. So this is about our last class, what is meant by counter and how many types of counters are there, what is meant by modulus of the counter, and what is meant by decade counter, how many number of states it will count, 10 states, and what is the need of up down counter, and why we prefer up down synchronous counter compared to the asynchronous counter. So these are the last class topics. Okay, now we are going to discuss about synchronous ring counter. Okay, and see here, our first topic is IC numbers of registers and counters. So before going to that, first I would like to explain you about ring counter. Okay, so already ripple counters are over. Ripple means asynchronous counters are called ripple counters. Now here it is called ring counter. Okay, so see here, while coming to the definition of ring counter, it will count the binary numbers. Okay, it will count. How it will count means every word having only single high bit. Okay, instead of counting. So till now either it may be synchronous counter or it may be asynchronous counter. How it will count? Already I told you, simply binary numbers 0, 1, 2, 3, 4. In sequence it will count the binary numbers like this: 0, 0, 1, 0. 0, 0, 1, 1, 0, 1, 0, 0. It follow one sequence: 0, 1, 2, 3, 4, 5. Like that it follow the sequence. All asynchronous and synchronous counters. But while coming to the ring counter, it will not follow the sequence. It will count the words having only single high bit. For example, for the first clock pulse, it will provide 0, 0, 1 means. For the second clock pulse, it will provide only 0, 0, 1, 0. This word having only 1, 1 now. For the third clock pulse, it will provide 0, 1, 0, 0. For the fourth clock pulse, it provide 1, 0, 0. So finally, the aim of this ring counter or the principle of this ring counter involves it provide the words that have only single high bit. See, here all are having only single bit. Single bit is there, single bit, single bit, single bit. All are having only one high bit. Okay, so this is about what? Ring counter. So what is the main theme of ring counter? It is a counter which is used to count the binary numbers not in the sequence, each and every word having only one high bit. Okay, and here the ring counter can be constructed with help of either maybe the D flip-flop or maybe the JK flip-flop. So see here, one important point is there. Till now, what are the counters we watched? They may be constructed with help of only JK flip-flops. But now these ring counters can also be constructed with help of D flip-flops. Okay, of course, if we want to interest to use the JK flip-flop, you use. Otherwise, it also may be constructed with help of D flip-flop. But either asynchronous ripple counters or mod counters, all are designed with the help of only JK flip-flop. But here, the ring counters are constructed with help of D flip-flops also. Okay, in addition to the JK flip-flop, D flip-flops are also used in the construction. And see here, the block diagram of ring counter. While coming to the block diagram, it is made with D flip-flop. So here in diagram, so this is made with what? D flip-flop. Input is D, output is Q. Input is D. So here how many number of flip-flops are there? Total 4. 1, 2, 3, 4. For the first flip-flop, what is the input? D0. What is the output? Q0. And for the second one, what is the input? D1. What is the output? Q1. For the third one, what is the input? D1. What is the output? Q2. So in this way, in construction of ring counter, here we are using D flip-flop. And see, the output of each flip-flop acts as the input for the next one. Output of each flip-flop acts as the input for the next one, and so on. And the output of last flip-flop is connected to the input of first one. This one is very, very important in the construction. Output of the last flip-flop is connected to the input of first one. So in this way, this fashion, okay, forms a ring. That's why this flip-flop is called ring counter. So in the construction, output of all previous stage flip-flops are connected to the input of previous ones. See once. So simply in this way, it looks like a ring. That's why this is called ring counter. And while coming to the second point, see here the clock pulse is applied externally to all the flip-flops at the same time. That's why this counter is a synchronous ring counter. So which type of ring counter is it? Synchronous. Why? Because the clock pulse is applied to all the flip-flops simultaneously. Once watch clearly. Okay. See here, all the flip-flops, the clock pulse must be applied externally at the same time. Okay. And while coming to the next point, the clear input also must be given to all the flip-flops except the first one. Okay. For the first one, we are connecting preset, and the remaining all are connected to the clear inputs. Okay. So this is called construction. So in construction of ring counter, which flip-flops are used here? D flip-flops are used here. Okay, in D flip-flop, what is the input? Is D and output is Q. So in D flip-flop, always the output follows the input. Means what? Whatever the input we are applied across the inputs, which bit means either high level or low level, which bit we are applied across the input, simply that is passed to the output. And here in ring counter, the output of the first flip-flop is always acts as an input for the next one, and so on for all the flip-flops. Output of first one acts as an input for the second one, and the output of second one acts as the input for the third one, and so in this way Q0 is connected to D1, Q1 is connected to D2, Q3 is connected to D3. And a very important point is the output of last stage flip-flop is connected to the input of first one. Output of last stage flip-flop is connected to the input of first one. So in this way, the flip-flops will provide a ring fashion, and it becomes a synchronous counter. Cause of here, clock pulse must be applied to all the flip-flops at the same time. Clock pulse must be applied to all the flip-flops at the same time, and the clear pulse is also applied to the flip-flops to clear the inputs if we want to require it. Okay, this is about what? Construction. And see here, while coming to the working, first Q0 output set up the D1 input. Which one will first set up the input? Q0. So next Q1, next Q3, and so on. So why means once you see here initially I applied one bit that is called preset bit. So here one bit is there now, preset bit. Initially we apply the preset bit. Cause of that Q, here it is equal to 1. Okay. So afterwards, then it is given to this Q0 is given to this bit will be given to the Q1. Okay. When Q0 is connected to D1, now Q0 becomes 0, Q2 becomes 0, Q3 becomes 0. Okay. For the first clock pulse, Q0 becomes 1. For the second clock pulse, this bit is transferred to Q1 and it becomes 0. And the remaining Q2 and Q3 also 0. And for the third clock pulse, this Q1 is transferred to Q2 and it also becomes 0. It is 0 as it is. And for the fourth clock pulse, this bit becomes transferred here, and these three are is equal to 0. So in this way the bits are transferred from one stage to other stage. Okay, so for the first clock pulse the bit Q0 is high, for the second clock pulse Q1 is high, for the third clock pulse Q2 is high, for the fourth clock pulse Q3 is high. Okay, and while coming to the first clock pulse, so here Q is equal to 0 0 1 0, and for the second clock pulse, after application of second clock pulse, Q is equal to 1 0 0 0. For the after the application of third clock pulse, it becomes 1 0 0 0, and after the fourth clock pulse it becomes 0 0 0 1. So in this way the counters will provide the counting, and here in the ring counter every time binary word having only 1 bit, and these ring counters are used for producing a ring word for timing different operation. The word is same, ring word is same, but it for different operations and then takes place in the computer. Okay, see, this is the truth table of our ring counter. While coming to the truth table, whatever the things explained in the operation, that is only reflected in the truth table. See here, for the first clock pulse, that is for the 0th clock pulse, the output of Q0 is 1. Okay, and for the next clock pulse the output of Q0 is 0, remaining also 0, but only the Q1 is 1, only the Q1 is 1. Okay, and while coming to the next clock pulse, the output of Q2 is only 1, remaining all are 0. And while coming to the next clock pulse, that is for the fourth clock pulse, here it is third but considered fourth clock pulse. Why? Because the counting is started from 0. For the fourth clock pulse, Q3 is 0 and the remaining all are 0. And if we apply next clock pulse, again Q0 becomes 1. And if I apply fifth clock pulse, then it becomes 0 0 1 0. If I apply sixth, means for every 4 clock pulses, after every 4 clock pulses, the same logic is provided, the same output is produced. That's why this counter is called ring counter. After every 4 clock pulses, the state of the flip-flops will be same. Okay, for 0 it is 0 0 1, for 4 it is 0 0 1, next for 8 it is 0 0 1. Means what? For every 3 cycles the output is same. At 0 it is equal to 0 0 1, for 5th clock pulse also it is 0 0 1, for 9th clock pulse also it is 0 0 1. Means what? If we require the same output after some interval, then the ring counters are used. Okay, if we would like to require the same output, okay, in the same intervals, then this kind of counters are required. Okay, and see here, this is the timing diagram. So before going to see the timing diagram, once you check, for the first clock Q0 is 1 and 0 0 0. It is 1 only. For the second it is same, means every state having 1 for one time and remaining 3 0. So see here, 3 only 1, only among 4 clock pulses only one time it is high. Okay, once see here clearly, for the first clock pulse, okay, for the first clock pulse, see here Q0 is high and the remaining are 0 0 0. And for the second clock pulse, see here, for the second clock pulse, here Q0 is 0 but Q1 is 1, Q1 is 1. Okay, and while coming to the Q2, Q3, these are 0 0, means first one 1 0 0 0. For the second clock pulse 0 1 0 0. For the third clock pulse 0 0 1, again it is equal to 0. Okay, for the fourth clock pulse it is 0 0 0 and 1. The next clock pulse it is 1, again all these are 0 0 0. Means after every 4 clock pulses the output should be revised. After every 4 clock pulses the output should be revised in the ring counter. That is the main advantage of the ring counter. And see here where the ring counters are used. So while coming to the applications indicate what? Where we are using the ring counter. Okay, so these ring counters are used in digital computers especially, so in digital computers. Okay, and also these are used in to execute instructions in the proper sequence. For example, if I would like to write a microcontroller program like this C1s, group some instructions I would like to write this. Add a next increment the register accumulator. Then again I would like to move a comma b. Next again add. So for after every 3 instructions, if the instructions are repeated, the group of instructions those are repeated is called subroutine. So during the subroutines, these counters are used. Means after 3 clock pulses, again the instructions are same. Okay, so where we are using our ring counters. Okay, and see here, these ring counters are especially used in digital computers and are also used in computers to execute the instructions in proper sequence. Okay, and these are also used to control the execution and are also used to control the execution. And see here, more applications are there. While coming to these counters, these are used in the frequency dividers and also used in digital clocks and also used in parallel to serial data conversion, that is called multiplexing, and also used in auto parking control systems. These are also used in auto parking. Means while the applications are same for all the counters. Okay, and see here, so these are the IC's numbers of different counters. These are the IC numbers of different counters. Why? Because all the counters are available in the form of IC only. So counters are available in the form of IC only. So here our table indicates which counter will produced by the which number of IC. So if IC number is there, that it becomes very easy to purchase. Even though in online, if we enter the IC number like 7490, simply which companies will provide the IC numbers, they appear directly. So instead of entering decade counter like that, if we placing it with IC number, means searching it with IC number for purchasing 7490, more number of Amazon, more online organizations will produce the counters with their prices. Okay, so here decade counters are produced with the IC number of 7490. What is the IC number of decade counter in TTL counter? Here the all counters are available by using TTL technology and also using CMOS technology. What is the full form of TTL? Transistor logic. Already I explained this is in your last classes. Okay, so TTL means decade counter is also produced with the help of CMOS technology and also with the help of TTL technology. And see here, in the decade counter, what is the IC number? 7490. Decade number is produced with the help of IC number what? 7490. And here this next IC 7492 will produce which counter? Divide by 12 counter. So now tell me, already in last class we have discussed about so many counter na? Divide by 12 counter means what in our language? Anybody? Okay, now I will. So here divide by 10 counter means simply divide by n counters are called mod counters. So here divide by 10 counter means what? Mod 12 counter. So mod counters are indicated with divide by n counters. Okay, mod counters are indicated with divide by n counters. Here the 7492 IC will able to produce divide by 12 counter na. So this divide by 12 means that is a mod 12 counter. Okay, so next IC is 7493. So 7493 will provide 4-bit asynchronous counter. 7493 will provide 4-bit asynchronous counter. 4-bit asynchronous means how many number of output states it provide? 16 states. 16 means from where to where? 0 to 15. And the next one is 74,160. So here it is a decade counter with asynchronous counter. So it is a decade counter with a asynchronous counter. Why? Because decade counters are available in asynchronous form as well as in synchronous form. If we enter the number 74160, it is a decade counter, but it is an asynchronous decade counter. For synchronous, other IC is there. Is it clear? So these are the different ICs to produce the counters. We'll see. Next series is 74161. 74161. So it will provide synchronous 4-bit counter. So it provides synchronous 4-bit counter. And see, 74190 is able to produce synchronous up-down decade counter. So 74190 produced what? Synchronous up-down decade counter. And while coming to the next series, next IC number 74192. So in 74192, which counter is available? It is a synchronous but BCD decade counter. So already in our last table, asynchronous decade counter is there now. Asynchronous decade is 74160. 74160 is asynchronous decade. 74192 is synchronous decade counter. Okay. And next IC number would produce 74390, that is asynchronous dual decade counter. Here there is a slight difference between synchronous BCD decade counter and asynchronous dual decade counter. So what is that main difference is, in synchronous BCD decade counter, it will provide the BCD numbers counting only. But 74390 decade counter will provide binary counting. Okay. While coming to the next group of ICs, these are CMOS counter ICs. So in CMOS counter ICs, the ICs are designed with the help of CMOS technology. What is the full form of CMOS? Complementary metal oxide semiconductor technology. So previous one is what? TTL, transistor logic is used in previous one, that is 74 series. But here in next 4000 series or 4500 series will provides us CMOS technology. What is meant by CMOS technology? Complementary metal oxide semiconductor device technology. So here 4510 will produce BCD up down counter, means it will count the numbers in BCD form. For example, if 10 0 means it will give 0001 and 000 like that, but it will give both direction counting. And next number 4516S. So this 4516S will provide binary up down counter, means this counter is able to count binary numbers. The BCD up down counter will able to count BCD numbers only, but binary up down counter will count binary numbers. And next one is dual up counter. Next one is what? 4518. So this is called what? Dual up counter. Two up counters are there in 4518. And see, while coming to the competitive examination, we are facing multiple choice questions now. From the ring counter also we facing, there is a possibility of questions from ring counter. First thing is, a ring counter is a, so must check the objectives. Is it triple counter, or is it synchronous counter, or it is a circular shift register, or none of the above? Logically you answer this question. Ring counter is a. So in ring counter what is going? Only one bit is shifted to all other flip-flops now. If Q0 is equal to 1, remaining are 0. In the second case, this bit Q0 bit is connected to D1. In third case, Q1 is shifted to, means only one bit is there initially. That one bit is shifted to flip-flop by flip-flop. It's only single bit is transferred to all the flip-flops. At a time, only one flip-flop having this bit. Second time it is transferred to second flip-flop. Third time it is transferred to third flip-flop. So that's why it is also called what? Circular shift register. That's why it is also called circular shift register. Is it clear? Okay. And see. And while coming to the important questions or previous question paper questions, so our question papers having 1 mark, 3 marks, 5 marks questions now. While coming to the 1 mark question, important thing is define ring counter. So how can we define? Tell me. So ring counters are the counters are used to count the words which having only single bits. Okay. What is meant by ring counter? It is a counter. It is used to count the clock pulses, but the words having only single bit, single I bit. Single bit means 1. And while coming to the ring counter, more one definition is also there. It is a counter. Here the output of one flip-flop acts as the input of next flip-flop. Output of one flip-flop acts as the input of next flip-flop. In this way, all the flip-flops are connected together. Output of first one connected to the second one input, second one output connected to the third, third output connected to the fourth, and finally the output of last flip-flop is connected to the input of first flip-flop. In this way, the outputs are connected to the inputs in a ring fashion. That's why it also called a ring counter. Okay. And while coming to the 5 marks question, what explain the working of ring counter with its diagram, with its logical diagram. So in ring counter, so which kind of flip-flops are used? That is a 1 mark question. Now tell me which kind, whether it may be constructed with the help of GK flip-flop or it also constructed with the help of D flip-flops. Ring counters, for the ring counters, choice is there. It may be constructed with the help of D flip-flops or it may be constructed with the help of JK flip-flop. So that is the speciality. But all other flip-flops are constructed with only JK. And in ring counter, one more advantage is there while observing the truth table. The ring counter will produce the same sequence after some clock pulses. For example, if it is a 3-bit ring counter, after every 3 clock pulses, the sequence is same. But 0 to 3, it will provide one sequence. Next 4 to 8, it will follow the previous sequence. And next 9 to 13 will follow the previous one. Like that, for every 4 clock pulses, the sequence is same. Okay, that is very, very important theme of our ring counter. And while coming to the applications of ring counter, sometimes it may be the 3 marks questions or sometimes it may be the 5 marks question. So whatever may be the question, you write full applications. It is used in digital clock pulses and it is used in frequency divide networks and it is used in industrial applications and also it used in some converters and used in digital computers. Okay, so these are the different applications of ring counters. And more one important question is there, list out the ICs belongs to the counters. Okay, list out the name of ICs, those produced different counters. So now you give the list. So while coming to the ICs, 2 kind of digital ICs are there. What is the first one? See here once. TTL family is there and CMOS family is there. You observe one thing here, TTL family will provide the IC number, the series is 74,000 series, okay, but CMOS is always started with 4,000 number, okay, 4 number. TTL is started from 7 and CMOS is started from 4. This is also one of the important question and that comes into the 3 marks. List out the IC numbers though produced counters, or if it is a 1 mark question, list like heading any 2 commonly used IC numbers, okay. If it is a 7, if the IC is started with 7, the number 7, then it under comes into which family? TTL family. If the IC is started with number 4, then the counters are under comes into CMOS family, okay. If it started with number 7, that goes into transistor logic family. If it is started with 4000, it under comes into CMOS logic family, okay. The counters are available in both families. In TTL family it is there, and also in CMOS family it is there. Once again you check the numbers. 7490 able to produce decade counter, 7492 produce divide by 12 counter, that is also called what? Mod counter. And 7493 4-bit asynchronous counter, and 74160 will provide decade counter with the asynchronous counter. Why? Because decade counters are available in synchronous form as well as in asynchronous form. Synchronous decade counters are there and asynchronous decade counters also there. And next the synchronous 4-bit counter IC number is 74161, and synchronous up down decade counter in last 74162 is synchronous decade, okay, asynchronous, that one 74162. Here 190 is synchronous decade. So what is the difference between synchronous and asynchronous decade? Synchronous will provide high speed, asynchronous will provide low speed, okay. And next one is 74192. It produce what? Synchronous BCD decade counter. Well, coming to the decade counters, there are 4 types: synchronous decade counter, asynchronous decade counter, synchronous BCD decade counter, synchronous up down decade counter, asynchronous decade counter, asynchronous dual decade counter, okay. Here it is 74390 series. It will produce asynchronous dual decade counter, okay. And CMOS family also will provide all the counters, especially it will provide the up down counters, okay. 4510 will provide BCD up down counter, and 4516 is provide binary up down counter, 4518 will provide dual up counter, okay. So these are the different ICs. They must produce different counters, okay, whether it may be the synchronous counters or it may be the asynchronous counters, okay. Once see the diagram. So once I would like to explain, see one key point is, so in ring counter, here it is constructed with D flip flop, but it is also possible to constructed it with JK flip flop also, okay. So in the, if it is constructed D with D flip flop, it looks like a register, okay. But if it is constructed with JK flip flop, if it is constructed with JK flip flop, J and K inputs are connected together and they will be given to the preset inputs. The first flip flop of J and K are connected together, second of J and K are connected together, and they are given to the output of next stage, okay. In ring counter, if D is equal to 0, Q is equal to 0, here D. Instead of this, if it is designed with JK flip flop, the diagram is like this. It is given to the pulse 1 high level signal, but these are given to the output of previous stage, okay, and this must be given to output of this given to the input of previous one. But in D flip-flop only one bit is there, so directly it is connected to D is connected, Q is connected to D, Q is connected to D, Q is connected to D in this way. But here two inputs are there, so the two inputs are tied together or connected together, and they will be applied to the two inputs are connected together and they are applied to the previous one high level input, okay. But both the operation is same, whether it may be the flip-flop, whether it may be constructed with help of D or it may be constructed with help of JK. In JK both J and K inputs are connected together. In D flip-flop only single input is there, but here we are using preset input. In D also you are using preset. In D flip-flop ring counter also using clock pulses. In JK also we are using clock pulse, and it is also synchronous counter. Clock pulse is applied to all the flip-flops simultaneously, and that is also synchronous. There also clock pulse is applied to all the flip-flops, and here the clear is connected to all the flip-flops. There also clear is connected to all the flip-flops. And while coming to the speed, here the clock pulse is applied to all the flip-flops, so the speed of the ring counter is very high compared to all other. So what is the main advantage of ring counter here? Once observe the truth table. Here it will provide the chain fashion output after every 3 clock pulses, okay, 0 1 2 3. After 3 we are getting again 0 0 0 1. Here the 0 0 0 0 word is missing. Why? Because the principle of ring counter is able to produce only one single bits, okay. The series containing only single bit, means single high level bit, all other is 0. If we are writing 0 0 0 0 means no output is there, so that condition is eliminated in the ring counter. But in all other synchronous and asynchronous counter, for one clock pulse, for the initial clock pulse, output of all flip-flop are 0. But here directly we are applying the preset, so that for the first clock pulse also first flip-flop will produce the outputs, okay. So it is the main advantage of here. It is the counting is started from bit 1. Each and every flip-flop having bit 1 at any stage, okay. So here for the first clock pulse, preset is applied to the first flip-flop, so that bit Q0 becomes 1. So here series 0 0 0 is not there at all the times. So that is the main advantage of what? Which flip-flop? That is the main advantage of this ring counter, okay. And here it should be which ring counter? It is a synchronous ring counter. And see, while coming to the timing diagram, so for the first clock pulse Q0 is 1, for the second clock pulse Q1 is 1, for the third clock pulse Q2 is 1, and for the last clock pulse Q4 is 1. And see, for the second, third, fourth clock pulses Q0 is 0, and for the first and third, fourth, Q1 is low. Next, for the first, second and fourth, Q2 is 0. Means every flip-flop will produce the output, high level output, only for one clock pulse. Produce the output for only one clock pulse. but the remaining clock pulse it is equal to 0. Only at one condition, at one clock pulse it produces the output, and for the remaining clock pulses it produces the 0 output. So this is the timing diagram of ring counter. The timing diagram and truth table are same for both ring counters, means it may be constructed with JK or it may be constructed with D. The timing diagram and truth table are same. Okay, now I would like to conclude the class.